Hello guys, and welcome back in Marketing Mix Modeling 101, everything you need to know about marketing mix modeling. I'm your host Christian, and this is the fourth episode of the series in which we will be covering the modeling phase, and specifically we will talk about feature engineering and modeling. I was thinking about including optimization in this episode too, but I ended up choosing to leave that to the next episode because there's a lot to talk about in this one, and I want you to really get the idea behind what the things that we will be talking about in this episode. So, of course, the contents of this episode will be mainly feature engineering and modeling, but more specifically, for the feature engineering part, we will talk about media transformations such as Adstock and saturations, as well as seasonality decomposition and modeling windows. Whereas for the modeling part, we will be covering modeling techniques, so we will get an idea of what you could be using during the modeling phase to handle different scenarios, and then we will understand how to evaluate and select a model, basically. So, first things first, feature engineering. Feature engineering is basically the action of transforming raw data to better represent reality. And the first thing that I want to talk to you about today is the Adstock Effect, which is based on the theory that the effects of advertising can lag and decay after an initial exposure. And to say this in a simpler way, not all effects of advertising are felt immediately. What this means? This means that imagine you do an ad on Facebook today, okay? On day one, today, where you launch your ad, you will have like 100% of the impact of the ad. That's the day that the ad will convert the most out of, okay? However, not all the people that will see your ad today will convert today, because maybe they weren't at all, maybe they were busy doing something else, and they could come back to your e-commerce like tomorrow or in 2 days or in 3 days and buy the next days. Okay, so your ad will have an effect in the following days, basically, and that's exactly what the Adstock effect tries to represent. So you will see that the impact is not like 100% on day one and then 0 on day two. It decays at a certain rate, okay? So you will have some impact on day 2, on day 3, on day 4, and so on, basically, up to a point where the impact, of course, will become 0. So, however, this is not the only way this could work, because you may have like not the full impact on day one, so you will have like 60-70% of the impact on day one, and then you will have like a peak in 2 days, 3 days after, because maybe you have like a high ticket product that you are selling. So most of the people will not be sure about buying right away once they see your ads on Facebook, but maybe they want to get back home and search for your e-commerce from their computer, get more information, think about it a little bit, and then buy. Or basically maybe they didn't need that item exactly that they saw their ads, but maybe they figured it out that they could use that like 3 days later. So that's another thing that could be happening, that we want to model with the Adstock effect. And there is an even more extreme case in which you may see like 0 impact on day one, and then the impact starts slowly showing the following days up to like having a peak like a week later maybe. And that's something that could easily be happening in case you are like doing ads on TV or radio, because people may be seeing your ads in a moment where they just can't buy. So maybe they are going to work in their car and they hear your ads on the radio. Maybe they are at a friend's house and your ad goes on TV. So the impact may really show up like a week later, the time that the ad was live. So that's another thing that could be happening, basically. And there are several approaches to model Adstock, but the main two things that you may want to learn about is geometric and Webull Adstock. And the main difference here is that geometric has a fixed decay rate. So it will say, okay, you are getting 100% of your impact on day one, and then you will lose like 40% of the impact per each day. So day one is 100%, day two is like 60%, day three is like 40% out of the 60% of day two, and so on, okay? So this is a fixed decay rate. Whereas Webull tries to be a little more realistic in what could be the decay effect, and so it allows you to basically have a more S-shaped curve where the the decay rate may not be linear, so you may have like a higher impact in the first 2-3 days and then a peak, a downfall, basically like after 3 days. So that tries to better represent reality, okay? And specifically, Weibo can be split into 2 subcategories, which is CDF and PDF. And the main difference here is that lines like the yellow one or the green one here can only be created with Weibo PDF because it handles the lagged effect. So it doesn't necessarily say that all the 100% of your impact must be on day one. Whereas with geometric and Weibo CDF, basically, you must start from 100% on day one and then slow down. Weibo PDF handles situations in which you may have your ads having like 0% impact on day one and then growing in the next day. So that's a really cool thing because it can better represent real world situations. And then once you get your ad stock right, you may want to move on to saturation curves, are also known as diminishing return. And the idea here is that each additional investment in advertising increases the response, but at a declining rate. So let's take a look at this plot on the right side here, okay? You will see this is like our TV spend, and specifically you will see our spend on TV on the x-axis below, and then on the y-axis you will see the response generated by the TV channel. And basically, as you can see, up from 0 up to 100,000 euros spent in TV, we got a linear response. So each and every like $50,000 we spend approximately drives us about $125,000 in response, okay? And that is linear because first 50,000 is bringing that, another 50,000 is bringing that, okay? Then we get into what we will call the optimal range, because here we are spending 50,000 more and the response generated is starting to lower down. So you will see that it's not even 100,000, it's like 25,000 in response generated. So the response is starting to slow down. Not so much that it doesn't make sense to spend on TV, but here is basically where you want to be in terms of spending, because then if you keep spending, you will find yourself in this part of the curve where basically you are over-investing. As you can see here, the returns are really starting to get lower and lower, basically up to a point where you even see it declines after a certain spend. And that's something that can happen because maybe you are so oversaturated, over investing on the channel that the returns, the response generated starts to getting basically declining. So where you want to be to maximize the return on investment is basically in the green area over here. If you have the ability to spend so much, if you can't go past this point where you start losing the linear response, you may want to spend anywhere in the linear response area, as that's what will drive you basically the most return on investments. And there are several different approaches to model saturation curves and to model diminishing returns. And the most common ones are logarithmic transformations, power transformation, and S-curve transformations. And I will specifically recommend you to maybe start with one of the first two, which are kind of easier to implement and understand, but then you may really want to take a look at the S-curve transformation as it's one of those that better represents real-world scenarios. And the next thing that we want to talk about is actually the seasonality decomposition, and specifically how to decompose time series, which in short, in practical terms, means deconstructing a time series into several components, such as trend, seasonality, holidays impact, and so on. And basically, what we are doing here is trying to get our 3 years of historical data and understand whether our business is growing. So we have a growing trend, we have a decreasing trend. So maybe it's not going so well. If the seasonality has any impact, so if there are days of the week in which we are selling less and more, if there are months of the year in which we are selling higher or lower, if there are basically years that were better compared to others and so on, we can model the impact that holidays have on our sales, which for a direct-to-consumer brand, maybe holidays like Christmas can have a really positive impact, whereas maybe you are a B2B company, so maybe the holidays are actually bringing less sales. That's something that you can find out during the seasonality decomposition analysis. And basically, if you were to do all of this by yourself, it will be kind of complicated and time consuming. There will involve quite a few maths and stuff like that. But thanks to the fact that that's something that everyone is doing, you have a lot of libraries and a lot of alternatives and things that basically can do everything for you. You only have to provide them with your data, basically, and they will find out everything else by yourself. And one thing that I want to mention here that you may want to take a look at and try yourself is Prophet. Prophet, it's a library available both in Python and R. It's actually an open source project developed by the data research team in Facebook that does everything we have just talked about in terms of decomposing time series, and actually more. There are like other features that you can be implementing in case you need those. And like we said, you only have to provide them the data and they will do the rest for you. And you will get an output that looks something like this. So up here, for instance, you have your seasonality decomposition, and you see we have data from like the end of 2016 up to the end of 2018, basically. And you see there is this clear pattern in seasonality where on the last months of the year, we sell a lot more. And then we go down where like right before summer, we have our lowest peak. We actually have a negative impact. In fact, it's driving negative impacts basically from February up to I will say the end of summer. So this is really cool because you understand whether you have a positive impact in seasonality. You see the last months of the year actually are bringing plus 400,000, whereas these months are driving minus 400,000 and so on, okay? So you see a clear, like this peak is stays here as well. This one, you can see it starts here, same thing, growing again. So you see there is clear seasonality in this data, and you can go even deeper and ask to understand whether there is some specific days of the week that are having positive or negative impact. So you may know that, okay, on weekend I'm not driving much. I may be better spending less money on weekend and then spending more on weekdays, for instance, and so on. And another thing that you see here is like holidays decomposition. So you will see that on some specific days where there is an holiday, the impact that this holiday brought to our business, and you can see that holidays on this business have like a crazy good impact because on holidays like this is probably Christmas right before January, you are having like plus 1 million in sales. Other holidays are driving a lot as well, 1 million here, 1 million here, 500,000 here. So holidays have a great impact on our sales. And this, one thing that we can get out of this is like, okay, a lot of impact on holidays, let's spend more, let's drive more people to our e-commerce and so on, okay? And once you are done with the decomposition, you may want to start understanding what your modeling window could be. And the idea behind this is basically selecting the right time period for your models, because MMMs are built on historical data, and we usually aim to get as much data as possible, like 3 years of historical data, 4 years of historical data, and so on. However, our marketing investments and general business situation may be really different now compared to 3 years ago, where maybe we were not spending as much on Facebook, and Facebook basically behaved a lot different, drove way different results, okay? I'll move myself on this part. So let's take a situation in which we have, for instance, 4 years of historical data in a data set. What we may want to do is use the whole 4 years of data to model for the seasonality decomposition, to understand whether we have a positive or negative trend, what's the impact of holidays, what's the impact of seasonality, and so on. But then, in order to better model reality, better represent the real and actual situation of our business, we may want to use only the last 6 months of data, for instance, for the other variables. And so what you are doing basically is building these two separate models. You will build the first, the one with the whole dataset during the seasonality decomposition, and then you will provide those outputs, the outputs generated by that seasonality decomposition analysis, as inputs to your main model where you have only your 6 months of data. And that's basically going to give you a real and clear idea of what your business looks like and what it has been like for the last period, basically, and what you can do to maximize your ROI in the next months or weeks. And once you got everything right in the feature engineering part, you have transformed your media variables, you have done your seasonality decomposition analysis, you have chosen your modeling windows on which you will be modeling, then you will start with the modeling phase, which is basically deriving the best possible equation for your business. And so there are different kind of modeling techniques that we will cover in this video. I'll move myself again on this other side of the screen. So first thing will be linear regression. We have already talked about linear regression, which is basically the easiest to implement and interpret kind of the modeling techniques that you can use. And the idea behind the linear regression is that you will have like an equation like this, okay? And specifically, I would like to put the attention for a second on the beta coefficients. So you see here, we have like this linear regression, which has been built on these 3 months of data. So the linear regression is working great because it's catching all the variations, okay? It's like 100% accurate. And how this works is that basically you will provide your linear regression with the data of these 3 months, and then you will have to derive the best possible coefficients, the beta ones, to actually generate this line, okay? And again, you would have to do that by yourself if we were in like 1970s, but thanks to the fact that we are in 2022, you will never have to do that in case you don't want, because there are plenty of libraries doing that for you, scikit-learn, Python, whatever in R, even Excel can do that for you if you do a linear regression in Excel, okay? So this is the concept behind the coefficients. And you may think, okay, this is a great model, this is like getting all the variations in my sales, but real world, probably the next months of data will look something like this. And you will start seeing your model being a lot less precise, and it will be so easy to just tilt this line a little on the lower side, and the model will get a lot better. But this is actually a common scenario that could happen in the modeling phase. If you have like too many data that's too specific, take not only that basically, but what could be happening, what is happening here specifically on these green dots that we are modeling on, is that our model is overfitting. It has learned so much about the data that we provided to the model that it's overfitting. But that means that the model is not doing so well in real world scenarios, like 1 month over, 2 months over, and so on. And one thing that we can do to handle such situations is using ridge regression. Ridge regression will probably derive a line like the yellow one over here that you see is less precise on the first data that we provide the model, but it's going to be a lot better in the future, because ridge regression is basically a linear regression that tries to generalize the model more. So you may have a little worse accuracy on the training dataset, but more often than not, it will work better for the data that the model didn't know about. And the idea behind ridge regression, first of all, ridge regression, so it's great to handle overfitting and multicollinearity as well, okay? Because the idea behind this is that you will have an additional alpha parameter which is used in the process of deriving the beta coefficients. So you won't actually see that in here, but in the formula used to derive the beta coefficients, you will have this alpha parameter that, in short, it penalizes the coefficients. So it will try to apply to the coefficients, basically we can say a worse value than what they would have, but in order to make the model more general and suit more kind of situation and prevent overfitting and prevent situations in which you may have multicollinearity. But, and this is ridge regression basically. Another thing that you may want to learn about is nested models, which are great to handle internal interactions between variables. And what does this mean? Okay, imagine you are doing your ads on TV and on search, like Google. Okay, both of these are driving sales, having a direct impact. So TV, you spend on TV, you drive sales. You spend on search, you drive sales. Okay, real world would look probably something like this. So you spend on TV, TV drives sales. You spend on search, search drives sales. However, some part of this spend on TV won't drive sales directly, but it will drive indirectly by driving more people to search for you. Because maybe I'm seeing stuff on TV, then I look for you on Google, and then I buy from Google, and it looks like the sales are coming from Google, but in reality, it's more like they are coming from TV, okay? So there is this indirect impact between the two. And that's something that you want to handle in order to have a more precise model. So what you can do is use nested modeling. And the idea behind nested modeling is that before doing the real model, where you want to model your sales, you will do like a submodel. In this submodel, your dependent variable will be your search. So you will be modeling how your search behaves based on other independent variables, such as your TV spend. And so you will basically be modeling the indirect impact on search provided by TV, or maybe other actions that you may do, like events and stuff like that. So you do this submodel first, and then you input the data of this submodel to the main model in order for it to both handle direct and indirect impact. And that's going to give you really much better results, where if you have a situation in which something like this is happening, of course. This is not really easy to see most of the times. You have to dig a little deeper probably to find out something like this. But if you do, nested modeling is probably what you want to implement to solve this. And now, there are a couple more advanced techniques I'd like to mention, but we will not cover these as they are, like I said, advanced techniques which you may not really find yourself using at the beginning of your marketing mix modeling journey, basically. But it's important that you know they exist at least, so that if you find situations in which they can be helpful, you know where to start looking for, okay? So the first thing is log linear. And the main difference here is that instead of a regression model, which is basically an additive model, we have our beta coefficients, we multiply for our axis, and then we add everything up and we get our revenue. Log linear works in a multiplicative way. So all the parts of our equations are basically multiplied together. So you will not have like a sum, but a multiplication, and that really is great to better catch specific scenarios that could be happening in your business. There's more to that. In fact, that's not just like beta 1 times x1 times beta 1 times x2. There's something more happening there, but to give you a general idea, the main difference is that this is a multiplicative approach instead of an additive one. And then the Bayesian regression is actually great in cases where you don't have much data. So like you are stuck with 3 months of data, you really need to do this modeling because you want to get information out of that. Bayesian regression can really be the way to go, because it works in linear regression works in a frequentistic approach. So they try to derive the equation based on things that keep happening and patterns in the data, basically. Bayesian works in a probabilistic way. So you basically, in short, provide your models with the probability that something will happen and less data, and then from those little data used alongside the probabilities that you provided the model, it will derive your equation. So that's great for a smaller data set. And basically, once you have your models done in maybe different ways, so you test out your linear regression alongside with Ridge, you test out some nested modeling, what you really want to do is being able to evaluate your model and select the right one. So you need some KPIs that are good to evaluate the models themselves. And the first thing that you want to look at is your R-square, which is basically the percentage of the variation in the dependent variable, so like your sales or conversion, described by the model. And it will look something like this, okay? imagine you have like your model, which is this, and all of these are your data. If your model catches the data exactly, you will have an R-square of 100%, which means that all the variations in the data are described by the model. However, you may find yourself in a situation like this, which is much more realistic. And so the line is close to the points, but it's not like exactly catching each and every one of them. So the idea here is that most of the variation is described by the model, but not exactly all of that. So we would have an R-square which is a little lower, like 92, 93%. And that's and that will give you basically an idea of the accuracy, general accuracy of the model, okay? Another thing that we might want to be looking at is our MAPE, or mean absolute percentage error, which is, in short, the accuracy of the predictions generated by the model. So, to give you an idea, let's say our model is predicting that we will do 95 conversions in the next week, okay? This is called Y hat. This thing on top is called Y hat. And basically, this is the predicted value of Y. So our model, our Y hat, the model has predicted 95 conversion next week. Then the week goes by, and we actually see that we generated 100 conversions in total. So there's a little difference between the 95 predicted and the 100 actually generated. And that means that we have a MAPE of 5%, which is basically how much our model was wrong in terms of the generated versus predicted values. Another KPI you may want to look at is called RMSE, or root mean square error, which is a measure of the error based on the mean square distance between each point and the model. I know this is tough to understand, but let's look at this plot, okay? You see the red dots is our data, and the line, the black line here is our regression line. Sorry, I spoiled the next the next slide. So you see these dotted lines show you that there is some distance between our line and our and the data. Okay, so we are going off some value basically, and that's the exact distance between the dots and the line. And we could basically just add everything up and get the overall error of the model, okay? But that wouldn't work right, because imagine a situation in which you have such errors like -1, 1, -1, 1. If we add this up, you get 0, which is not correct, because clearly if you see something like this is not 0. This is probably some degree, there is clearly some degree of error. So summing them up wouldn't work, because if you have negative and positive, you may end up in situations like this. So what we do is we square the values like this, so that everything gets positive, and you have like 1, 1, 1, 1, 1. And once you get to sum them, mean them, you get something that's a lot more, that makes a lot more sense, which is basically 4. Then we put it under a root again, because now this is clearly an easy situation where it's 4, so it's somewhat a small number. But basically, to return to a value that makes sense in our model, we will then root the square values. And this is another great way to understand the error, basically, of your model on the training dataset, basically. And then, another couple things that I want to mention in this episode is F-Statistic and P-Value. And both of these two variables tell you about the statistical significance, respectively, for the F-statistic of the overall model and for the p-value of each variable. So you will get a clear idea whether it makes sense to include a variable, exclude a variable, because it doesn't have statistical significance. There's no evidence, basically, that this variable, is somewhat related to the actual model, basically. So this is all for this episode. It has been full of notions and things that you may or may have not heard about earlier. So I will close this up here in order not to add too much to the contents. And of course, as always, guys, if you have any kind of questions, if there's anything that was unclear or you would like to learn more about, let us know down in the comment, reach out on LinkedIn, you will find references in the description below. And And we would love to hear your feedbacks on this course and all other contents that you find on our YouTube channel, Cassandra. So if you're curious about learning more, if you want to stay up to date with new episodes coming up and other contents that we are sharing on data science, marketing mix modeling, and statistics, just subscribe to our channel, guys, and you will be basically updated once new stuff comes out. I'll see you in the next episode, in which we will talk specifically about how to turn insights into actions, so how we can get decisions about what to do based on the modeling phase, and we will talk about the optimization phase as well before going into that. So thank you so much, guys, for watching this. See you in the next one. Bye.